Okay, I'm going to write up these solutions pretty quick. Not too much annotation. I think some of you are waiting for this to take that quiz. So anyways, all right, location 1, it's all PEG. Location 2, we've decreased our PEG by about half. The rest has gone into kinetic. All right, location 3, it's all kinetic. Gotta make sure we have 4 adding up. Location 4, we started to hit the brakes. Maybe we are half kinetic and half internal. And location 5, it's all internal. All right, so conservation of energy. So the PEG at location 1 equals the sum of the PEG in K at 2, which equals the K at 3, which equals the sum of kinetic internal at 4, which equals the total internal at 5. So ultimately, we've gone from gravitational potential to internal. All right, this one here, the ball dropped, starts off all gravitational. All right, and now it's fallen down about, about a third. So location 2, it's probably about a third kinetics. So I'll say 1.5 kinetics, 2.5 PEG, something like that. All right, now location 3, it's about a third of the way off the ground, so I'll say 1.5 PEG. But we built up some internal energy because it's hit the ground. Now the evidence for that is 4. Right? I'm going to come back to location 3. Location 4, we got to have at location 4 the same PEG as 2. Right? So it's got to have the same PEG as location 2. So I'll say 2.5. All right? And that's it. There's no kinetic. So that other 1.5 has to be an internal. Now where did that internal energy came from? Well, it came from when it hit the ground at 3. So you got to have that same 1.5 here. So the kinetic energy here, if I say this is 1.5, 1.5, 3, that only leaves me with a little bit of kinetic energy here. So this has to add up to 4, right? So that's a little bit of a problem because this kinetic energy has to be bigger than 2. So this is really got to be like 2 units of kinetic energy here. All right. Then I got 1.5, 1.5. That adds up to too much. So, I probably need to readjust my graphs a little bit, right? So, this PEG here, I'll have to reduce for 3 maybe. KE has to be bigger than this one. It's not going to be much bigger, but it is going to be bigger. So I probably should reduce this kinetic energy here, make this a little bigger here. As long as it roughly adds up to 4, we'll be good. All right. Now over here, I'm just going to get going here. Gravitational energy at the top, PEG at the top. Now I should be writing UG, right? That's what we use for gravitational potential energy in AP Physics C. Equals mgh, so it's UG equals 0.250 kilograms times 10 newtons per kilogram times the height of 0.50 meters. So 0.25 times 10 times 0.5 is 1.25 joules. Internal energy built up when sliding down the ramp is 20% of the initial energy, so 0. Internal at the bottom equals 0.2 times 1.25, which is going to equal 0.25 joules of internal energy built up. Determine the kinetic energy. KE at the bottom is 80% of 1.25, which will end up being 1.0 joules. I know it's 1.0 because also it's the other way to get it is KE at the bottom is equal to the UG at the top, and I should be calling it just capital K, not KE. UG at the bottom minus the internal energy buildup, right? Equals 1.2. This is top. 0.25 joules minus 0.25 joules equals 1.00 joules. I don't want to really make that 3 sig figs, but oh well. Determine the speed of the car at the bottom of the ramp. Well, once you know the kinetic energy at the bottom of the ramp, you just 1/2 mv squared. So 1.0 joules equals 1/2 of 0.25 kilograms times v squared. 2 times 1 divided by 0.25 equals v squared. Right? 2 divided by 2.25 is 8. So radical 8 equals v, or 2.8 at the bottom. You know, you can put the bot on there as well for bottom. Energy at the bottom is 1/2 mv squared at the bottom. Oh, that was totally off the page. Sorry about that. There it is. Went through that. 1/2 mv squared. Okay, good to go. On to the next one. It's not 87 minutes, and it's 9.3 minutes. I did this one in the video. Power is change in energy over time, which in this case is change in UG over time, which is mg delta H over T, which we usually just call mgh. So power, which is capital P, is 70 kilograms times 10 newtons per kilogram times 380 meters. It's just the vertical height change. 9.3 minutes times 60 seconds per minute per 1 minute, so the minutes cancel. So 70 times 10 times 380 divided by 9.3 times 60, make sure you put parentheses on the bottom, 477 watts. All right. Remote control train consumes 150 joules of electrical energy to get up to a speed of 5 meters per second. How much internal energy has the system increased? Okay, so I don't have an equation for internal energy. I mean, I do, but so we got a tank here, toy tank. Right? So it rolls along up to a speed of 5 meters per second. So the KE of the tank, capital K, is 1/2 of 2.0 kilograms times 5 meters per second squared, 25. Kinetic energy of the tank is 25 joules, right? Let's cancel. 25 joules of kinetic energy in the tank. So where did all the energy go? All right, well, it started off U electric equals K plus U internal energy. I should say U internal here, so we'll often write that as this, U internal, not E internal. So that means internal energy buildup must have been a total of 125 joules, right? This is 150, this is 25. Most of it went into heat. Most of the initial electrical energy that we consumed went into heat and inefficiencies. Now, clearly, that's not exactly a force of friction, right? But we'll practice with it. So work equals force times distance, right? And, you know, F average, work done equals force average times distance. Or you know, so this work here is only the work due to friction, right? And that equals U internal only. It's only U internal. So we get 125 joules of energy lost due to some sort of frictional force. This is fictitious, right? There's no real, you know, single force here. So it's times 4.0 meters, 125 divided by 4 is about 31 newtons. if it was a single frictional force doing this over 4 meters, it'd be 31 newtons of force. But it really isn't. It's much more complex than that. All right, this one here, number 6. People were asking for this one. That is not right. That height we actually don't know. That's something we have to find. This height is 0.10 meters. I fixed that on the printed one online eventually. So, determine the velocity of the cart when it's at a height of 0.1 meters. Well, what type of energy we've got? I'm going to call this location 1, location 2, location 3. So, the US at location 1 equals the UG at 1 plus the kinetic energy at 1. That's what we've got going on here. Alright, so 1/2 kx squared equals mgh1 plus 1/2 mv1, v2, sorry. Now say that's x1. Alright, so we're looking for v here. So we know 1/2 of 250 newtons per meter times 0.10 meters squared equals 1.0 kilograms times 10 newtons per kilogram times 0.10 meters plus 1/2 of 1.0 kilogram times V2 squared. So I'm going to go ahead and figure out the initial spring energy. There's really nothing to cancel out here and solve, so I'm just going to go ahead and solve this times 0.1 squared. 1.25 joules equals 10, it's going to be 1.0 joules plus that. You know, some people would like to do this all piecemeal, you know. So bring this over here, it ends up being 0.25 times 2 divided by 1 equals v squared. Take the square root of both sides. I wrote too big up here, so I'm running out of space. You get v equals 0.77, I want to say. 2 times 0.25. 0.71. 0.71 meters per second is its speed at location 2. Alright, so 0.25 joules left for kinetic. There you go. So up the ramp now. So this is one of these things they like to do on the AP exam where it's a pretty easy energy calculation, but they give you this weird geometry, 15 degrees. Ultimately, we need to figure out this height, right? Because that's where it's going to go a certain height off the ground to stop. So that 1.25 joules of initial energy turns into mgh3. So that 1.25 is always the total energy, right? This is the total energy, right? So if it's all gravitational at location 3, then I can just use that, set it equal to that. So 1.25 joules equals it's 1 kilogram, 1.0 kg times 10 newtons per kilogram times the height, which is what we don't know. So 1.25, this is 1, right? Or sorry, 10. All right, so I get height equals 0.125 meters, or 0.13 meters to 2 sig figs. So it's gone up a few more centimeters vertically, which at 15 degrees corresponds to a pretty decent length farther up the ramp, actually. So the height ends up being 0.13 here. All right, so I'm going to get rid of that, 0.13 meters. So our triangle here, the opposite side is 0.13. We need the hypotenuse here. So we know the opposite. So use down here, sine of 15 equals 0.13 meters divided by d, which is the hypotenuse. So this is rare that we actually use trig to actually find a physical length, right? Usually we're doing 2.50 meters. Usually we are doing this with forces and stuff. Okay, so it's kind of interesting. We're actually figuring out a physical length here for something rather than a force or a component of a velocity or something like that. So that's it for that. I'll get this posted right now. This video posted right now, just real quick. So those of you that didn't turn in the quiz, there you go. I'll get this posted and got no excuses.